Maxine today. Yeah, one more key. Yeah. So maybe we have one. Okay, great. So today we're very happy to have Pouya Asadi joining us from Santa Cruz. Pouya did his PhD under David Shi at Rutgers before he went off to MIT and then Oregon, and now he's just started at Santa Cruz. And today he's going to be telling us about taming axion rotation, dark vector-like confinement for axiogenesis.
Thanks a lot. And thank you very much for the invitation and for having me here. First time I'm actually in Minnesota. It's a really nice place. You guys also have a very fancy here. So as Robert said, I'm going to talk about axiogenesis. I will clarify what that term means in a second. I'm probably one of the last few young people that is not working on axions. So this is my entry into the field. But as a result of that, there are new things that I want to learn, and I appreciate any feedback you have on these papers in collaboration with David Cincinnates and Stefania. And there's going to be two papers on these things soon. So this is not working. Okay, this is going to be the outline of my talk. Hopefully, by the time I finish the intro, the rest of the outline will be more clear, and please feel free to ask questions at any point. So, okay, it's still the BSM talk, so I gotta start from talking about the standard model and how how great and how amazing it is, and explains a lot of phenomena across many different scales. That said, it has some shortcomings. And you guys have heard the spiel probably 1,000 times by now. But some of the biggest shortcomings is that, well, the biggest anomaly we have in the data is the dark matter, that we don't have a particle physics explanation for. A standard model doesn't provide a dark matter candidate, enough dark matter candidate for us. And we also don't know, and a standard model cannot explain the excess of baryon over anti-baryon in an inflationary universe. These are really the two biggest shortcomings of a standard model in the data. And I'm not even going to touch dark energy, but we know that these things make up our universe, but we don't know anything about where they really, these abundances, where they came from. So, of course, when you have a situation like this, it makes sense to ask yourself, how can I explain these observations? What kind of models can we write down to explain these experimental anomalies? And another reasonable approach to also have and complement this is to think about funny patterns, curious patterns in your theories. That doesn't necessarily mean there has to be some new particle or something, but it's just something that doesn't feel right, something that you feel like this structure is there for some reason. It can't just be completely random. This is just a simple way of expressing the naturalness notion that we have all over the place. And a standard model has many unnatural facets to it. But one of these curious patterns that I think doesn't get enough attention is already shown in this figure. I know Robert and Tony think about these things sometimes. It's the fact that the abundance of dark matter and the standard model are actually very close to each other, very closer than you a priori would have guessed. To just shorten this point, let me remind you of some very basic facts about where these abundances come from. On the standard model side, the scale of QCD actually directly controls how much, or feeds into how much, how big the energy density of the visible matter is. And the scale of QCD through dimensional transmutation is determined as a function of some parameter in the UV, some order 1 parameter in UV that exponentially enters the calculation of the scale of QCD. And that parameter could very easily be like a factor of a few, 2 or 3 different. And that, since QCD is exponentially sensitive to it, that gives rise to orders of magnitude change in a scale of QCD. QCD scale and the proton mass could be very easily 2, 3, or 4 orders of magnitude different in every direction. Same as, and that controls how much energy density we have in the visibles. Same with the dark matter side. In any different dark matter model you consider, let's say WIMP for a second, just for this slide, You always hear the word that Wim's mass could span large orders of magnitude, and its cross-section that controls its freeze-out and abundance will be able to span many orders of magnitude as well, like tens of orders of magnitude. So there is really no reason for these abundances to be exactly where they are. They could be between a range of tens of orders of magnitude anywhere, but for whatever reason, they're right on top of each other. This could all be a coincidence, but if it's a coincidence, it's hell of a coincidence. This ratio that could be 10 to minus 10 or 20 easily is 1, order 1. Why? I think it's a good guide for trying to do model building beyond the standard model. And in order to actually make this point even sharper, let me remind you that this similarity of abundances is really the strongest and probably the only hint we have, empirical hint we have for dark matter and a standard model having interactions. People do all these searches and come up with new ways of looking for dark matter standard model interaction. The only reason we have to think that interaction exists is that these abundances are close. So if you actually come up with a model that can explain this similarity in a nice way, in a reasonable way, it could motivate a lot of searches and become the main target of a lot of different searches. And if you ask me, I will argue that there aren't any models that fully explain this coincidence in the literature, but there are a lot of cogenesis models. And the first step to get to a full solution to the coincidence problem is building a cogenesis model. What do I mean by cogenesis? And I'm making a distinction between a solution to the coincidence problem, I call them coincidence models, and cogenesis models. The difference is that cogenesis means some setup that gives you the dark matter and baryon asymmetry, but you get the ratio to be comparable to each other only in a measure zero part of your parameter space. You have to tune some parameter, be in a very specific corner of parameter space to get the ratio order 1. Where a full honest-to-God solution to the coincidence problem should be a mechanism that generically gives you the abundances being comparable to each other across a large swath of this parameter space. So I want to make that distinction, and when you do that, you will see that a lot of models that people say, oh, could be a complete solution to the coincidence problem is not, like asymmetric dark matter. It's just a cogenesis model. Nonetheless, since it's a hard problem, it makes sense to start thinking about cogenesis model. And what I want to do in this talk is to tell you about, or try to answer this question. Can QCD axion dark matter be embedded in a cogenesis model? QCD axion, which I'll pay lip service to in the next slide, is a motivated model of dark matter. And I want to see if it can fit inside this picture, and at least as a cogenesis model, could give us a way of getting these abundances comparable to each other. Okay? Yeah.
So can you say more about the footnote down the bottom about anthropics? And you think this ratio is anthropic?
I think it's not. And you and I have a discussion about it. We are in agreement with that. This is essentially for Dan Cooper.
Yeah.
I'm giving this talk next week at Wisconsin, and I'm trying to be, well, I'm antagonizing Dan with this one.
So there's no
Frank Wilczek and Anthony Aguirre had a paper from 2005 or so arguing that there is, essentially saying that if you have a lot more dark matter, you rip the disk apart, and if you didn't have enough dark matter, you don't get enough of them to form the seed of a galaxy. I don't completely buy their arguments, and it's very heuristic. I think we're at the stage that we can actually do simulations for a lot of these things. And I think you and I talked about this, there is room for doing some quantitative calculation and see if there is any anthropic reason or not. Regardless, I'm not an anthropic person. I don't like it. There is nothing unscientific about it. I give it that.
Yeah.
I don't like the defeatism that comes with it. Okay.
The anthropic argument could not fix the ratio to be order 1, right? But in fact, we cannot have too much dark matter or have too little to support that. So I think
we
that
could have
is,
zero down.
but maybe the upper bound. So from that paper, I think the analysis is dark matter over luminous matter ratio better not be more than 1,000.
I mean, Yeah, okay. They put, if you put, they have a plot, and in there, I think they argue that you could be within a range of 1,000 or something. So yeah, even entropic in that level doesn't work for this. We're not, that's Jen's argument, essentially. That's what he's saying.
You agree.
I'm against using anthropic to make a precision argument. I'm saying the argument Pouya gave here is correct. In principle, the ratio of dark matter to our luminous matter can be exponentially distributed anyway, but at least the anthropic cut it off that exponential distribution to the solid finite range, which make the problem less severe.
And my point is that I think it could actually, they're still optimistic about that cutoff in their paper, and it could be more quantitative. But we are on the same team. We needed Dan Hooper here to bash on this. Yeah.
Very quick.
Oh, geez. Why are we living here on Earth and not on Mercury? Because things are suitable for life here and not on Mercury. By the same virtue, maybe, and this is the way I thought, maybe we have a lot of different patches in our universe where the parameters of the fundamental theory are different. Somewhere we have more cosmological constant and dark energy, somewhere less dark matter, and so on. We're just in a patch that has the right number to support life. Just the same way that we are in Earth and not on Mercury. That's gist of the argument, and if you want to learn more about it, Weinberg is the first person that wrote a paper on this, and the only anthropic paper I really like. So a single author paper by Weinberg from late 80s. Okay, so I want to remind you again, this is the question that we're going to go with. And actually, before that, how many of you have worked on axions? Okay, good. I thought I will be the only person in the room that hasn't worked on axions. You guys have worked on it and it didn't raise your hand. I know you. So, okay, let me just very briefly give you an introduction to what axion is. You probably have heard, many of you have heard it many times. In a standard model, you can have a term like this, with the GG dual being the field strength of the color force, the strong force. And this parameter theta, that could be anywhere between 0 and 2 pi, it's a phase. Yet, we know that it's very, very small. Why? This is a curious pattern. There's a naturalness problem. It's not natural to be like this. And this is known as a strong CP problem. And it has two really cute solutions. One of them is QCD axion, which essentially promotes this thing to a dynamical field from the breaking of some global symmetry that is anomalous under SU3. And this interaction after QCD phase transition gives a potential to that dynamical field. It's a cosine potential, and its minimum is where that whole combo, the bare parameter and the dynamical field, go to 0. So dynamically, your theory prefers going to theta equals 0. And that explains why theta, well, we don't see theta being non-zero. People quickly realize that this axion actually redshifts like matter, can be a dark matter candidate. And if you consider the discussion I had in the previous slide, you should ask, can it actually be embedded in a cogenesis model? Can it have anything to do with the baryon asymmetry in the universe as well, or not? And people have tried to build models. I think the term axiogenesis was coined by Keisuke and Raymond Koh 6-7 years ago. It's a really creative and cute idea. Unfortunately, the minimal version doesn't work. And I'm going to review that in this talk from a different angle that Raymond and Keisuke have talked about. Hopefully that will be useful for you, but it doesn't work because when you generate enough baryon asymmetry, you just produce too much dark matter, too much axions. And hopefully I will clarify why that happens in the minimal axiogenesis model. But then, based on that, what I will try to show is that if the friction that QCD axion feels in the early universe was different, we could avoid that overclosure problem. Overclosure means it's just making too much dark matter. And I just put a very minimal extension of the model, essentially having two axions and a new vector-like confining force that solves the problem. This is just to give you a hint of where we are going. I'll just build toward these points, but this is the target we get to. And this opens up new parameter space for searches. This is the usual axion parameter space that, well, I'm starting to get used to seeing this picture. But we argue that on top of the QCD axion, if we have another axion that lives here, we can actually have a working cogenesis model without overclosing the universe. This is the manipula that I'm going to build this talk towards, okay? And the model definitely has a lot of different signals, not only here, but also at colliders. So this is what I'm gonna show during this talk. But in order to build there, I will start by reviewing the basics of sphaleron physics that are the underlying physics responsible for all of these in a non-abelian gauge theory, and how they contribute to baryon asymmetry, how they contribute to a friction that axion feels, and how we can actually fix the minimal axiogenesis model. So I know the last slide was very fast. That was just a summary, executive summary. But if everything is clear, I'm just going to start.
So at the end, just to understand, we're solving the two problems there, right? Just the dark matter, strong CP.
Yeah. Dark matter, strong CP, and baryon.
So you're going to solve all three.
All three. Yes, I will do that. That's why we need this guy.
Yeah, yeah. So you are solved.
Yes, yes. I'm gonna give you a working cogenesis model. The only reason I keep saying cogenesis, not coincidence, is that I don't think these are full solution of coincidence problem, but it's the first step. I do the three of them. I solve the three problems together. You're good? Okay. Things may get a little bit technical. Apologies in advance. I really thought I'm gonna be the dumbest person about axions here. But let's just get into it. So we have this term in a Lagrangian, some non-abelian gauge field with theta, and from now on, theta is a dynamical field. It's an axion. Very early on in 80s, people realized that when you have these non-abelian gauge fields, that operator is essentially a total derivative and can be written as a total derivative of some current, a Chern-Simons current, it's called. And in a homogeneous universe, that tells me that if you have a non-zero expectation value for that operator, that essentially changes that Chern-Simons number, the conserved number attached to this current. And this Chern-Simons number labels different vacuum of non-abelian gauge fields. And there are field configurations that take you from one vacuum to another. So the usual schematic picture is something like this. You have some different topologically distinct vacuum of a gauge field. And the sphaleron is something that takes you from one vacuum to another. What I want to do is actually calculate the rate with which this hopping between these vacuum take place. It's just the sphaleron rate happening and how this Chern-Simons number changes. And you will see that this is actually related to the baryon asymmetry that I'm going to talk about. So we want to calculate that. And the very easy way to do it is to just think about, this is a field configuration in finite temperature field theory in the early universe. You can think about thermodynamics and changes in free energy and all. I'm not going to go into that detail. You can show that this expectation value is given by something like this. And the two parameters that I want to draw your attention to are theta dot here and these guys here. So theta dot is essentially the time derivative of that theta term, the dynamical field. It keeps rotating between 0 and 2 pi. We call it rotation of axion. And that contributes to the energetics of sphalerons, just because it acts like a chemical potential for Chern-Simons number. But also different fermion asymmetries. M here is the asymmetry of every fermion, J fermion, that is charged under the same non-abelian gauge field. Each fermion contributes to this energetics of a sphaleron. The reason for that is for each of the wild fermion you consider, chiral fermion you consider that are charged under this gauge field, you have an anomaly. You have a triangle anomaly for that fermion number, just that's chiral. And when you have something, and when you have that anomaly, that means this operator appears in the divergence of that current. So when something gives you non-zero value of that operator, you get a non-zero divergence for your fermion number, and it appears in there. I'll be happy to give you actually more detailed discussion of here. These are something that for some people is just completely a standard, for some people is absolutely alien, but I'm happy to tell you more about it. But I will use this equation, and this is how sphalerons contribute in the background of a rotating theta to the baryon different fermion asymmetries. And based on this argument I just gave you, you can see that this whole thing should contribute to the time derivative of different asymmetries. Okay, so yeah, sphalerons contribute to different wild fermions asymmetries. And what I want to do now is write down the Boltzmann equation that governs the asymmetry of different fermions in our model. Okay, so far this is a standard thing that you will see in an electroweak baryogenesis talk. So this is one process that contributes to fermion asymmetries in the background of a rotating theta. There are another simpler processes that I'm going to call them chirality frequent processes. In a standard model at high energy, they're essentially a scattering of 2 to 2 scattering of some fermion with the Higgs in the standard model thermal bath. So this process, you can actually take one left-handed fermion in a standard model and turn it into a right-handed fermion, like an L in a standard model into an E. And that means you change the number density or the asymmetries of the L field and the E field, for instance. So they will appear in the Boltzmann equations governing these asymmetries. And to give you an example, if I think about the Boltzmann equation of a right-handed lepton of generation G in a standard model, this is it. This is the Liouville part of the Boltzmann equation, Liouville operator. Some finite temperature effects give you these combos here. And then you have a contribution from these processes that are proportional to the asymmetry of different fields in a standard model. So this process acts like a washout terms. Whenever you have a contribution in the Boltzmann equation of some asymmetry that is proportional to some number densities themselves, we call them the washout terms, just because if there is any asymmetry for that particle, they wash it away. So these processes contribute to the asymmetries as well. And we're going to come back to these guys. These guys actually, this is super straightforward and simple stuff, but this thing is going to be the central star of the show in the model that I'm going to write down later on. So, okay, we have 2 set of processes, sphalerons and these chirality flipping processes that contribute to the Boltzmann equation for different fermion asymmetries in a standard model. You can go ahead and write the gigantic Boltzmann equations. I don't want you to go into all the details here, but just to sketch it, the first equation, for instance, I'm showing the equation that is governing the asymmetry of a left-handed quark, Q's in a standard model of generation G. They have contribution from the Yukawa couplings of the up-type and down-type quarks. Those are this type of processes with the Q going to up or down-type quarks. And you have contribution from the sphalerons of the strong force and the weak force, just because Q is charged under both these non-abelian gauge fields. And you can do it for all the 5 type of fermions in a standard model. That's your Boltzmann equations. What I want to draw your attention to is that the only source term in these equations is theta bar. The only term that is not proportional to some particle asymmetry itself are terms that have theta bar. So that's the only source term. If we turn it off, we get equations that are essentially in a standard model equations for these asymmetries, and we don't generate any asymmetry for different fermions. So all the asymmetries we get in the end are going to be proportional to theta dot. Okay, of course. Now we can go ahead and solve these Boltzmann equations. They look scary if you haven't seen them before, but they're not that hard to solve. In fact, you don't even need to solve the dynamics. You can just calculate the equilibrium state by just setting the right-hand sides here equal to 0. If you solve these equations, you will see that for whatever initial value, you go to those equilibrium states. So we solve essentially an algebraic set of equations that are over constrained and find the expression for all the different asymmetries, all the quarks, leptons, Higgs, and so on. And then you, from those asymmetries, you add them up to find the baryon asymmetry that we get in the end. And once you put all the values of couplings there, you get an expression like this, proportional to the theta dot at the onset of electroweak phase transition. ESFO stands for electroweak sphaleron freeze out. I hate that abbreviation, but my collaborator insists on it, and we are being consistent with the literature, but whatever, sure. So this is the asymmetry you get, and numerically you can check that. If you want to get the observed asymmetry in the universe, you want your theta dot to be 5 keV at the onset of electroweak phase transition. You can just put the numbers in there and see you will get that. So I'm gonna do an IR study. So I'm gonna assume at the electroweak scale, we have this rotation. I wanted to say a few words about getting the UV construction in an extra dimensional model. I won't have time for that. I'll be happy to tell you more about it after the talk. But we're gonna assume that we have something in the UV that generates this this rotation for some axions. And that will give us the baryon asymmetry side of it, okay? But the problem is that whenever in the minimal axiogenesis, when you have this, you will overproduce dark matter later on. How do we circumvent that? To see that, let me remind you that the same sphaleron physics that actually affects the baryon asymmetries in these equations appears in the equation of motion of the QCD as well. So if you write down the QCD's equation of motion in the UV, it's just going to be an equation like this, just because in your Lagrangian you had theta GG2. And so that's the equation of motion for the axion. And this guy, I earlier showed you what the expression for that is. It's something in terms of theta dot and different fermion asymmetries. And the point in the previous section was that different fermion asymmetries are proportional to theta dot. So this whole thing will be proportional to theta dot. So I can write it as something like this. Yeah.
This equation is also used in leptogenesis.
Yeah.
Turning on that.
Yes, I'm turning it off. No leptogenesis.
So you don't have any right hand.
No.
They would also contribute to that equation.
It could. And in fact, that was the first fix that Keisuke and Raymond, and I think Lawrence Hall came up with that. They said, oh, okay, we have this thing and let's add leptogenesis on top of it. And
Because that's going to provide like a term like the theta dot.
Yep. Well, that
Or
provides
is it another term? Is it just another term?
in the Boltzmann equation, essentially that would be a new term that generates baryon asymmetry,
Yeah.
something that violates B minus L.
Yeah,
essentially.
yeah.
Yeah. I didn't want to do that. It's
Yeah,
just
yeah.
more minimal here.
Yeah, that's it.
I mean, not to crap on the idea, but I felt it was a little bit of cheat, just a little bit. No, I'm not saying it's a cheat, but yeah, I shouldn't say that it's a cheat. But I want to see if this mechanism works. It's like if you add that, you're adding one new component per problem. I want to just keep everything contained and see if I can get the problem out of these.
But their motivation, yes, is that you know that you have and I guess that's
Probably, although, I mean, we can say that we don't know what mass scale right-handed neutrinos are, and we don't even know, well, never mind, let's not get
but
into
it
that.
makes that.
Exactly.
You're doing
I'm doing it different. I think you had a paper with Keisuke and Raymond as well, but you guys were thinking about heavy axions.
Yeah.
So you're not thinking about this side of it. So, okay. This is equation of motion of axion, as I told you, and once you do put in the equations I showed earlier, you see that the sphalerons essentially give rise to a term like this in the equation of motion of axion. And this is a friction term, proportional to theta dot. Just like the Hubble, it provides you with a source of friction. Okay, the axion, you can think of it as a harmonic oscillator. if there was a potential with theta squared. And that guy is just the friction force that dissipates energy, takes energy out of this system. And since we could calculate the asymmetries of different fields as a function of theta dot, we could actually calculate this epsilon c, this friction term that the QCD axion feels, and it's given by an expression like this. So gamma c is the QCD sphaleron rate. It can measure at lattice, temperature, and these Yukawas are the standard model Yukawa couplings of up and down types of different generations G. And I really like this formula, and this actually starts to get into the intuition that we need for our working model. Notice that, first of all, the factor of 1 is just from pure QCD, but this part is the one that I want to talk about. These contributions arise from the asymmetries of different fermions that will be a function of different Yukawas. They appear in the Boltzmann equations for different fermions. And they have a very funny functional dependence here. This expression will be dominated by the smallest Yukawa of a standard model. This is like putting together a bunch of resistors in parallel. The smallest one dominates it. And you can show that it actually, the friction goes like this. So if the smallest Yukawa becomes smaller, the friction becomes smaller and smaller. Okay, it's a little bit funny, but just important to keep in mind. And it goes like TQ, just because this guy has dimension 3 and T is the only dimensional parameter. So, okay.
But then, sorry, back at neutrinos and neutrinos.
Good, no, because this is coming from everything that talks to QCD sphaleron. Yeah, thank you. Good clarifying questions. Yeah.
First, so, even some people talk about massless UY.
Okay, yeah, good.
So that would totally like not fit.
Yeah, if you have a massless upward, you don't need any of this bullshit.
Yeah.
So
But then you work mass to 0, then this goes up.
if this doesn't blow up, I guess you gotta take the limit properly. It goes to 0, actually.
Up to 0.
It goes to 0 because 1 inverse, 2 inverse.
Sorry.
Yeah, it's a very funky functional dependence. And this is essentially the intuition that I feel like would have helped in the original Axiogenesis paper. At least helped me once I realized it. I realized why the original thing had, well, despite being brilliant, had this problem.
The lighter the Yukawa, the less friction. Right?
Yes, yes.
So it takes less effort to go between different transcenders.
Exactly. Because there is no washout.
Right. Massless case, the transcendence number is not really a physical quantity in the system, so it takes no effort.
Good. Maybe I wasn't explicit about it. Thank you for clarifying it. Yeah.
That's that.
Yeah, I should, for other people that haven't thought about a strong CP, there are 3 solutions really for it. The QCD axion, something I like called, well, discrete space-time symmetry-based solutions. Let's not go there. But also, if one of the parts in the standard model, like upward, was massless, this parameter theta would not be physical. And all these discussions would be moot. So, and I hear contradicting claims that that solution is ruled out or not, because we can't directly measure the upward mass. But right now, I'm going with just the original, well, at least seems to be the mainstream thing that Yukawa cannot be 0. So see, that's where I stand, but then I talked to, I think, Aida or someone else, and they were saying that not really. And I am not the judge of that.
There's a PR.
There are a lot of PRLs that are wrong. So, okay, assuming up Yukawa is not 0, we're gonna go with this, but in that limit, the friction also disappears.
Question?
Yeah.
So in the previous slide, when you showed the result, like Li is proportional to theta dot,
Right.
solve the Boltzmann equations.
Right.
Did you consider theta dot as some external like source? Like,
You can actually include it in these equations once you have the
but
UV
the
model.
final conclusion.
The final conclusion, of course, doesn't change. Again, the piece of that you care about is to have this rotation at the electroweak scale. I'm going with that because I'm doing an IR approach, IR model building. In the original paper, they come up with a way of actually getting this rotation. It's very cute, but it has a little bit of problem with the quality problem, in that it has a quality problem. And I think I think we have a fix for that when thinking about the extra dimension UV axions. And that's the UV part that I don't have time to talk about. But yeah, happy to talk about that later on. For now, we just assume that we have that velocity at the electrons.
But I mean, like the friction we'll discuss in the next slide, would that affect the solution of this equation?
The friction, no, the friction we get when we assume, okay, maybe I gotta be clear about line of logic. If we assume we have this velocity, we get this asymmetry, but also an axion that goes around like this feels a friction, okay? And that friction is just given by, well, since all the asymmetries are proportional to theta, it's given by this thing. So I know it's a little bit counterintuitive to wrap your head around. I'm still trying. Everything else is clear? Good, just ask question, please, if I'm going fast or saying something nonsense. So, okay. Friction dominated by the smallest Yukawa goes like TQ. So this friction in a standard model was arising from these processes. I mean, that's the chirality flipping process above the Higgs web in the electroweak symmetry restored phase, and it was going like TQ. Importantly, that means that that friction over Hubble friction scales like T in a radiation dominant universe. So as time passes and we go to lower temperature, the friction becomes less and less relevant in QCD plus axion. What if we had another sector that had chirality flipping processes like this? We had some dark sector with heavy vector-like quarks that had a heavy vector-like mass. That happens below the electroweak scale in a standard model as well, because we don't have a background Higgs and different quarks have masses. In that case, you can go through the same set of calculation and you will see that this is the friction term you get. Very similar to the other term, except instead of Yukawas that were there, now you have the masses of different quarks. Let's say in a standard model, for instance, you would have these masses of different quarks appearing. And you have a T2 instead of T4 there. So the whole thing, since you have these dimension full parameter here, the whole friction now would go like T instead of TQ. And importantly, in a radiation dominant universe, we assume is the case between electroweak scale and QCD scale, it goes like 1 over T. So the friction arising from vector-like fermions scales differently than chiral fermions, and it becomes more important at low temperatures. Okay, that's the important intuition. And with that, we can actually look at, for instance, how this friction is scaled in a standard model. Here I'm showing the ratio of the friction over Hubble with some fixed Pechet-Queen scale as a function of temperature. Time goes to the right, we go to lower temperatures. The purple line and the black line and the dashed line is the one I want to talk about. The purple line is just a pure QCD. That's just this factor 1 in these friction terms. The black line is the friction in a standard model. So this is the electroweak phase transition. Above that, we have chiral quarks. Chirality flipping is through chiral interaction with Higgs. And the friction actually becomes less and less as we go to lower temperatures, as I argued in the previous slide here. So a standard model friction is also very low. That's where this ratio is 1, the dashed gray line. But the standard model friction is much less than Hubble. The culprit is the small Yukawa of the up quark. The smaller the Yukawa, the lower the friction. So if I actually have a velocity of 5 keV at this point to get the baryogenesis going and get the right asymmetries, this velocity will be sustained to lower temperatures. I mean, it redshifts with Hubble, but it doesn't feel extra friction in front of it. and it maintains too much kinetic energy. And by the time you reach QCD scale, you just have too much energy and you overproduce axions. I'm not going to go into that. Keisuke and Raymond and Lawrence all had a paper on it, kinetic misalignment. It's a really cute idea. But anyway, since we don't have friction in the standard model, we maintain velocity, we overclose the universe. But gee, if only standard model fermions had a heavy vector-like mass, the story would be completely different. Let's say we had a fermion, the lightest fermion in a standard model, had mass 100 GeV, and it was a vector-like mass. And the discussion I had earlier from the vector-like fermions and friction, the friction goes like this. It's a small at high temperature, it grows at lower temperatures. That's a little bit too much, but if that new quark, well, the lightest quark in the sector has, say, 1 GeV, and everything else is the same as a standard model, its friction would be very small at the time of electroweak phase transition. It's smaller than Hubble. But then below that, it becomes more and more important. And it could actually dissipate energy out of the axion. So a vector-like confining sector, by the way, my favorite DSM models, actually could help shed energy out of the axion. So we're going to utilize that to develop a model to actually explain, well, actually avoid this overclosure problem. Yes.
So could this be KSVZ?
Good. In Prince, no, because the friction is dominated by the lightest quark charged under that gauge group. And we already have the up quark. And that up quark dominates the friction. That was the point of this equation. If you assume, for instance, look at this. If I assume I have 1 over m up squared plus 1 over m KSVZ quark squared, 1 over up squared dominates. This is much larger. So unfortunately, in QCD, we can't do anything with it because we know the masses of the quarks modulo that asterisk. And that asterisk actually even makes the QCD friction lower. So we really can't get it out of our QCD. We really need some new confinements, new sources of friction for that. But that's not actually crazy to accommodate. So I'm gonna, let's consider this Lagrangian. I have 2 axions now instead of 1. And I also introduce, we have our QCD with GC field strength, and we introduced a new confining force as well. We call it GD. And we have our 2 axions. One of them is Pechequin is anomalous under our side, so only talks to our QCD. The other one is anomalous under both our side and the other side. Again, this is something that easily you can think about 2 branes in the extra dimension, a bunch of chiral fermions. You can actually get these things easily in the UV model. Well, you should trust me on that. Sorry, I'm not going to include it in the talk. But this setup, actually, I'm going to show that works for us and can allow for dissipation of energy. I mean, as long as this combination has a large rotational velocity at electroweak scale, we will get the baryon asymmetry. And then there will be friction from this side that takes energy out of the axions, avoid overclosure. You may actually scold and say 2 axions, now you're just adding too many things. But let me remind you that if you talk to a lot of the string theorists, they actually say that it's very natural to have multiple axions, multiple light axion-like particles. It's a reasonable IR manifestation of a lot of compactifications in string theory. So these guys and a vector-like dark sector is really just not unnatural in these setups. Okay? Yeah.
Can you tell us more details about the fate of the dark sector particles? Like what's the fate of like fermion? Is it
good? I will get to that. Good. Thank you very much. Good. Give me 2 slides. I want to talk about this dynamics of these fields. No, actually, in that parameter space, I will show that in most of it, it is 100% of dark matter, but it doesn't have to be. I should also say that there are some dark quarks here to get the right friction, but I will get to that in a second. So let me tell you, let me tell you, let's look at the equation of motion of these axions and think about just how they evolve below the electroweak scale. I'm going to assume at the electroweak scale, I mean, they don't have any potential, either of them. That's their equation of motion. And I'm going to assume the second one, theta 2, is rotating with that 5 keV thing. And the first one is not rotating. There are other scenarios you can consider. You can accommodate these in different UV models, but let's just go with this. This is intuitively very simple. This is the equation of motion essentially at around electroweak scale. And I'm including the friction from QCD just to show that it couples these two. So it takes some velocity from here to there, but it's very small, as we talked about it. QCD friction is very small. As we go to lower temperatures, the friction from the dark side starts becoming important. I introduced some heavy vector-like dark fermion that gives us friction that grows at low temperature. And also, eventually, we reach the scale of the dark confinement, somewhere between electroweak scale and QCD. We actually have a wide range that it works. And when that happens, we get a potential for the second guy through the non-perturbative effects. We get a cosine potential for theta 2, and in the equation of motion, it looks like a sine. And essentially, that picture looks like something like this, like the potential of the second axion. Now, it's not flat. You have some potential. The first one is still at its place, barely moving, no potential. We go to lower temperatures, QCD susceptibility becomes important eventually. And you get this term in both equation of motions that couples these two things, these two equations. Just because, remember, this is the Lagrangian. So the susceptibility of QCD generates a potential for these two, this combination together. So, okay, we get this, and this means that, I mean, this guy's potential doesn't change much because QCD scale lambda C, chi C is smaller than chi D. But QCD axion theta 1 does get a potential now. And importantly, the potential is time dependent because theta 2 is still rotating around in its field space and it keeps going up and down. And that enters in there. So there is a time-dependent potential for theta 1. Eventually, while all of this is happening, still that guy is in play. We have a friction that takes energy out of the second one, and the first one is coupled to it as well. The energy is drained out of this system to the point that the second one now cannot go over the bump in its potential and gets trapped at the bottom at some point and just oscillates there. And as it oscillates, it also keeps shedding energy into the dark gluons and dark glue balls. The QCD axion theta 1 also, when its potential stays at its place, it's not rotating anymore, and it also loses energy, well, by being coupled to theta 2 and theta 2 having some friction. So this is the intuitive picture of what will happen in this setup, in this model I told you. Starting from the electroweak scale and going down to QCD scale. Of course, we're going to solve these equations numerically, carefully, but I'm not going to go through the solution of it. It's the intuition that we get from the solution. This is the what the solution would look like. Questions? Yeah.
Can you go back to the first slide where you show that to get separate in there? Is there any reason why can't I just define theta 1 plus theta 2 to be the QCD axis?
Effectively, we are doing that. In the end, when I want to think about the searches, I got to think about the mass eigenstates. And that's there, as in this guy, actually this gauge field dominates the mass for this guy. And the other mass eigenstate become very aligned with theta 1. So, but really, effectively, when we solve it, we do that. We consider this combination and some other combination that talks to this guy, and solve the equations for those guys. They're actually easier to solve.
So you're saying basically I can do the 1 plus 2 QCD.
Yeah.
That will not affect cosmology.
It shouldn't, right? It shouldn't. In the end, you have these two fields. You should get the same cosmology regardless of how you call them. in the end, you get some mass eigenstates. You gotta care about what are the mass eigenstates at the search. Tony, yeah, you're good. So, okay, that was a lot of words. I hope things are clear. I'm really just talking about some oscillators and just their movement and some potential, nothing complicated. Okay, so once we, let me remind you what we are doing. We assume we start with this velocity of the second axion at electroweak scale to generate the baryon asymmetry check on the baryogenesis. I argued that we can have dark vector-like confinement where the friction on the second axion grows below the electroweak scale, and it can deplete the energy out of the axion. So check on reducing the energy density of the axion system. But then that energy goes somewhere, goes to the dark glue balls of the new gauge field that we have. We better get rid of them, otherwise they will overclose the universe. And we can do that through their portal to a standard model. So these are the, and for that we need to introduce new vector-like quarks. So we will have some new vector-like quarks that are charged under both a standard model and the dark gauge group that allow the blue balls to decay to a standard model, say photons, before BBN, to not mess up with BBN. And we will also introduce some other lighter dark quarks that are charged only under the dark sector, and they can go much lighter, because these guys control the friction that the second axion feels. Remember, all I wanted to do was get some situation where the friction that this axion feels is small at electroweak scale and it grows later on. And to get that, we need a second quark that sometimes it's below 100 GeV. And well, it can't be charged under a standard model in that mass range because of that. So we need two sets of quarks, and that's it. The whole thing works. And
wait, sorry, but there is an overlapping range here.
there is a okay. There
Is there a
thank
slim
you.
region where you
That's some okay. These are, by the way, off the press. Like last week, the mass ranges. We actually did a scan over these things to give you the money plots right now. I want to say that no, I'm just being conservative in the range that I'm writing down here. I think this range is actually all below 100 GeV.
Oh,
I think.
okay.
Actually below even 10 GeV.
Okay.
But I have to go back and check.
Okay.
So yeah, maybe actually that's a good point. I should really say 10 GeV here.
Okay.
I'm almost sure there is nothing. It's just the scan. So, okay, you do this, you get this parameter space. And there is a lot happening in here. So let me unpack what's going on. Here I'm showing the axion mass versus the Pecha-Quinn breaking scale axion constant F. For the two axions we have, the theta-1 axion, this is the usual QCD line, and the mass eigenstate becomes very aligned with the QCD line. And the second axion that, well, we'll have to live in this region for the whole thing to work. I'll comment on that in a second. I'm essentially putting the two parameter space of these two axions on top of each other. The gray regions are bounds that we have from different observations. I'll comment on the light gray regions in a second. But essentially, what you should take away from this plot is that if you have a QCD axion somewhere in this line, and a theta-2 with that 5 keV velocity at electroweak scale that lives somewhere in here, depending on different parameters of the model, like dark lambda Q, well, lambda controls the mass, like the dark quark mass, you can actually get the cogenesis working. We solved the equation, we found the abundance of theta-1 and theta-2, and the baryon asymmetry that is determined by theta dot, and the whole thing works. But why does this region look like this? Let me comment on its shape. The right border here, which already is ruled out, by the right border in this plot, it doesn't go forever, it's cut off, because as you go to larger axion masses, for a fixed F, you're going to larger lambdas, lambda Ds. And at some point, lambda d becomes so large, it becomes close to the electroweak scale. And at that point, the friction just becomes very large on the second axion. So it loses its rotation before it can do the electroweak before electroweak phase transition. So it cannot generate the asymmetries. The left border of this side is cut off because as you go to lower this side, again, with fixed M, with fixed F, you're going to lower lambda D values. That means the lifetime of the glue balls become larger and larger, and they start decaying after BBN if you go too far in that direction. And in fact, for the gluons to decay, the heavier quark, actually the mass of that guy cannot be arbitrarily large. So if the mass of the heavy dark quark is charged under the standard model as well is 4.2 GeV, that's the parameter space. If it was 1 TeV, you go only up to this point. And if it was 4, you go only up to that point. So you do need some particle that is charged under both sides, the standard model and dark side, in the hundreds of GeV to get this thing working. And that means you can actually look for this thing at collider. So that's a cool feature of the setup. And the bottom region comes from essentially the overclosure. As you go to larger Fs, you get a smaller and a smaller friction. Friction was epsilon over F squared. And when the friction is too small, you don't shed enough energy from this axion system. The friction is small, so you overclose the universe. At this border, you essentially, theta 2 is all your dark matter, to your question. What fraction of dark matter is the visible theta 1 or theta 2? At this border, it's essentially all the second axion. Yeah, but everything in the bulk, it's actually be a subcomponent of dark matter, and most of it comes on the QCD axion. The different points in this region map to different points on here. This is the plot in progress. So if you have comments on how to improve this money plot, I really appreciate the feedback. I should also say that you play around with some details of the model. You even can open up parameter space around here, but I was just not showing it because, well, the scenario is different. I can comment on that later. It just gets complicated. So, yeah.
You have a dark sector which confines.
Right.
Does the topological susceptibility of that dark sector affect our QCD axiom?
I mean, yeah, that is the whole point of the thing here. This is the topological susceptibility of the dark sector.
I'm talking about our QCD axiom, the mass of our.
Right, yeah, I gotta remember this. It doesn't directly talk to the.
Well, it's a linear combination.
It's
theta 1. It's theta.
Oh, that was on our side. Good, thank you. Theta 1 plus theta 2 is our QCD. The other QCD is just theta 2.
Yeah, but the topological susceptibility will give a contribution to theta 2.
Right.
But then the axiom mass eigens that contains
Oh yeah,
a
yeah.
portion of theta.
That's what I was saying, that you have to calculate the mass eigenstate and you have to diagonalize that mass matrix.
But
Sure.
Do you get masses which differ from?
Yeah. Does that make sense? I mean, that's why.
Let me see your plot.
Yeah, there is not just one line. Depending on what F2 is,
So you actually shift
it gets shifted a little bit, and it goes in the right direction.
Yeah, you make
Yes, exactly. Yeah. Okay. Thank you. I should take a note of that. So let me just say that, okay, I did say that theta 2 becomes a subcomponent of dark matter. Let me comment on these gray regions. These are regions, in these regions, you do get bounce. Well, in this region, you actually have thermally produce a lot of axions from like gluon going to axion gluon, for instance. And the whole story changes and you overproduce axions. So that part is ruled out. These quite, light gray regions are regions that you get bounce from axion to photon, but those bounds assume a dark matter abundance for the axion. In our case, in this region, since actually axion would be a subcomponent of dark matter, theta 2 would be a subcomponent of dark matter. The bound don't really just, you gotta be careful about applying the bounds, and we haven't gotten to do that. In fact, I don't even know, these are JWST bounds. Some people are claiming this is what JWST can give you. So I have to understand these things myself. If you guys have worked on these things, I really appreciate a comment on it. The phenomenology of these axions are completely new to me.
It's also a little bit confusing too, because you have both axions that are playing their respective subcomponents, right?
Right.
So to the extent that like the theta 2 component goes to 0 and the other one is all of the dark matter, then those are still the constraints that you want to show on this plot, right? But it's just not touching that part of parameter space.
That's
Or like, it's like, yeah, there's a lot of juggling pieces because you have two sets of axions
Yeah.
you're doing with.
I really think we are trying to jam too many things in one plot. Maybe we should have two separate plots. But yeah, we are brainstorming on
Yeah.
this. I appreciate any feedback you have. If you're essentially the first people that are hearing this talk and hearing me talking about axions, so I'm sorry.
So you're assuming.
Oh, good. It's pre. I'm essentially assuming pre-inflation. It's almost what?
So it's, I think it's almost post-inflation scenario.
It's actually it's a pre. Well, I didn't comment on the
The constant is like F A with G. And so are you assuming very low scale inflation?
You can say that.
You
Yeah.
have.
Yeah,
so
yeah,
you're
yeah.
assuming low scale
If it wants to be a pre-inflation, yes, scale of inflation has to be below these things. Yes, but I really didn't comment on the UV side of the story. But it can be, yes, it can be a pre-inflation like that. I like pre-inflation because really well, actually, there's another way you can get that. The extra dimension axion models are really pre-inflation models. Even if the scale of inflation is higher, they are pre-inflation
If you
models.
consider experimental axiom here, it's very difficult to have a kick.
Good.
Kick requires metric and complex scale.
Good, good. Yeah, we should talk about that.
Okay.
I can run the idea I have on how you can actually get that in an extra dimensional
So
axion.
this is just contribution from background zero swing. When you were saying the axiom darkening, you just take into account background oscillating.
Yeah, I'm assuming we have the background oscillation.
That's the only contribution that you consider.
Yes, yeah,
Okay.
yeah.
Yeah.
But
We can talk more, yeah.
yeah, we should definitely talk more about that. Okay, another set of experiments that are relevant for these in this part of parameter space are ones that don't care having axion make up all your dark matter, like light shining through the wall and so on. So I think those would be cool for this new region we find, but their sensitivity, if I understand correctly, are like a few orders of magnitude above this. They're not there yet. We have collider signals, as I told you, just because we need something to talk to the dark blue balls on our side to deplete them. And if there are other signals that I'm actually not showing here and I haven't thought about, I really appreciate the feedback. We should chat about it later on. So let me just summarize. What I wanted to actually, what I started with was the importance of the coincidence problem as a guide for BSM model building. I think this problem really needs more attention and give us, it's a big prize if you come up with a working coincidence problem solution. And in that line, I tried to actually think about axions as a source of generating baryon asymmetry as well. And I argued that the QCD axion, the minimal version that we talked about, because of the friction that QCD axion feels, we don't have the pieces that we need for a working axiogenesis setup. We just, whenever we get the right baryon asymmetry, we overclose the universe because the friction in QCD axion is too small. But if we have a vector-like confining dark sector with its axion coming in as well, it can actually solve the problem and give us the right dark matter abundance and baryon asymmetry, so solve the QCD problem. With the two axion mass eigenstates living here and here. And it defines a new region for different searches. And I think it's a region that's not as explored as some of the other regions. And it's worth thinking about the phenomenology. So that's all I have today. Thank you.
To just do something super naive and like write down like axion photon coupling.
Mhm.
Like what do you have an intuition for like what the scale and the scaling is that would appear on like this friction?
Axion photon coupling, I mean, depends on the UV, of course, famously, depending on what field content you have, you get different E and N's. I don't know if
Yeah.
it makes sense. This is the usual, like, this is the
Or no,
super
sorry, I
normal
meant like
now.
kind of on the left plot, because like a large part of, if I understood correctly, I'm trying to like re-summarize your pieces in my head now.
Okay,
And so a large part of the story is the need to introduce the new axion and the new confining sector and the new vector-like forks.
that's right.
And it's all motivated by like this friction.
Yes.
So my very, very stupid question is like, there are dumber things that I can write down,
Mhm.
like an axion FF tilde. And like, where does that show up on this plot? If that makes sense. Is that like
so
way
you're
down
asking-
here?
You're asking what friction does the axion feels from the sphalerons, for instance, of the weak force?
Yeah.
Good, yeah, it's gonna be proportional to,
And I don't know off the,
it's gonna be smaller than the QCD axion by at least alpha weak over alpha strong to fifth power, 4 power, that there's a big, well, there
Oh,
used to
right.
be. It's suppressed by a lot more. Because the frictions, actually. This is counterintuitive. The friction terms go like the sphaleron rate. And these sphaleron rates for every gauge group, it's for every SUN goes like n times alpha to the n to the 5, alpha to the 5, I think, times t to the 4. And alpha big over alpha strong to the 5. That's
okay, so yeah, you really have.
I think so.
So everything, so the point of the UV models is just to explain this 5K. Initial rotation. What's the point of having?
Good. Allowing you to have 5 keV, but then dissipate energy below that. Have friction that takes energy out of it, below electronics.
But are you trying to explain the 5K?
No. That's what we said. That I assume we start with 5 keV at the electrode.
Okay, but then you have to explain in UV
How you generate that. I agree, and that's the extra dimension side of it that I
So
will.
that's the reason why you're trying
UV model. Exactly.
to explain this 5K.
Exactly.
And what's the just if you can just summarize, what's the minimal? So you're saying it has to be an extra dimension?
Okay, yeah, my obsession with extra dimension model comes from one, I like them, two, a quality problem. And so it could be any other axion. Essentially, you could just say that, yeah, it could be KSVZ or DFSZ axions, absolutely fine. And you can just get these things in those setup. You just have to have only vector-like and heavy enough vector-like dark quarks to get the right friction. So there is nothing wrong with those guys. That's right. That's right. Actually, yeah. Let me. Yeah. Okay. Fine. Well, yeah. I want to solve more. Yeah. I'm indoctrinated by Matt Rees that extra dimension axions are good axions. But yeah. Okay. Yeah. I'm not going to talk about this.
And it's basically just flat.
Essentially, yeah. This is just saying that, well, not two, but this is a figure I took from Giovanni's paper. If you have 4 scalars on the 2 branes, I can gauge 2 of their the combination of their U1s, and 2 combinations remain as Pechi-Quinn breaking. And then I can play around with the bulk masses of different field charge under these things to give me different level of Pechi-Quinn breaking. So that I have enough Pechi-Quinn breaking for one of them to get rolled out and move around. Well, there is an extra wrinkle here, but the other one that has a very high quality Pechi-Quinn breaking. So I want the Q1 theta 1 to have a high Pechiquin quality thing. That's why we are exploring this extra dimension side of it. But again, this is a sketch of what's going to happen. It's not something that I haven't written down explicitly right now.
But this allows for natural value of the rotation.
I should see that. I should see that. I know it's you need the breaking to be large. So
Because I know that's an issue.
that's one issue that
Because they try to symmetry. Try to set up the initial conditions of axial rotation.
Right.
That's symmetry.
yeah, they needed even super Planckian, I think, field excursion.
So
Yeah.
you're gonna have to eventually have something that's I guess what
Mhm.
that's the reason to go construction.
That exactly is the reason I'm going. That and quality problem
Yeah.
is the reason I'm going there.
I would say that's the main.
That's the main thing. Okay, fair enough, fair enough. The UV,
Quality will always be fixed up by adding on an add-on. Right? You can fix something.
maybe I'm old school. I wanted to keep it minimal.
That's what this is. Module,
That's true. That's true.
which is
That's
fine.
true.
But I'm
Yeah.
saying it's
It's a pattern of the task. That's your fixer introduce new quality problem. Have you estimated that?
Wait, hold on. It introduces new quality problem on what? Sorry.
So solving the strong CP problem.
I mean, the reason I want to first of all, this is something I want to do. Okay. It was supposed to be done last week, but whatever. The reason I'm doing this is that I think it could actually solve the quality problem because of what I told Tom. I can have the Pechiquin that is corresponding to theta 1 to actually be very exponentially suppressed. If the bulk mass of some field charge under gauge groups here is heavy compared to the size of the two brains. So I think it's, I mean, this is the
actual dimension to solve the quality.
Yes, I'm using
Let's
that.
go back to your potential.
Yeah. This is really hard. You meant, sorry.
So we can stare at this. You assume theta 2 solve the dark strong CP and theta 1, and theta 2 become have some expectation value on the our QC sector. So there's no feedback. There's no back action from theta 2.
Exactly.
So theta 1 just solve it.
Yes.
Okay? The
Yes.
question
Good.
is, if I have back action, does the dark QCD potential leak into our QCD potential? This place
Mhm.
by a little bit and introduce a new quality.
But the only place, I mean, the potential I get.
Because
for
theta 1 and theta 2 are mixing, and the theta 2 is breaking these two sectors. So theta 2 will bring some of the dark QCD potential.
Yeah, but I mean, I can have like theta 1 plus theta 2, and I have chi d 1 minus cos theta 2, right? Oh, sorry. So I guess so if, I mean, whatever happens to theta 2, maybe I'm actually being naive about this. This will help me. Whatever happens to theta 2, and it has its Pechiquin breaking, the Pechiquin breaking for theta 2, in the end, the potential that theta 1 feels is just this cosine potential. Treat theta 2 and whatever value it's getting as like bare theta naught value plus something. Treat that as just your bare effective theta bare value. Theta 1 goes to a value that cancels this combination, right?
Again, you assume theta 2 is non-dynamic. Put theta 2 into some fixed value.
Okay.
Now theta 2 actually is a dynamical field.
Mhm.
Sees that the dark QCD potential. So it's
Right.
really that.
Right.
QCD. At a higher order, so it displays the minimum
Mhm.
little bit.
Right.
dynamically.
Right.
So it would be nice to estimate whether there's.
Right, and you're saying, I mean, if I just say that theta 1 then adjusts itself to actually cancel that,
That's
that's
a non-dynamical point of view.
Mhm.
So you here you say theta 2 just choose its expectation value from that potential.
Right.
But however, theta 2 as a dynamical field also sees that potential
Yeah,
and
yeah.
bring it to the theta 1 because theta 1 mixes.
No, I was, okay, good. Yeah, I was thinking about it at the level of the VEV, essentially.
Yeah,
And at the
yeah.
level of the VEV, I mean, it makes sense. But you're saying I got to worry about the fluctuations.
Right. Because
Mhm.
you treat theta 2 as background field. Talk about
Right.
that's not entirely.
That's not good. Okay, let's talk about, let's talk more about this. This will be helpful.
One should estimate.
Yeah, actually, let's talk about how to estimate this. Like, I have thought about it at the VEV level thing, not at the level of fluctuation. So that would be important. Thank you.
Second question, can go back to your final thought. So for your model, and let's say if I didn't include this dark QCD design,
Right.
what would your QCD axiom?
What? Oh, right. Yeah, good. It actually will be somewhere around here. Well, depend on the UV again, as you know. Well, no,
Right,
sorry.
I want to have same UV as your theta 1 second.
No, sorry. I take it back. It's not the UV thing. It's just that the line is determined by the fact that lambda is equal to m times f square root. So it's gonna be somewhere near these lines. I
know it's near, but the question is whether it's above or below.
I'm gonna say it's on this side of it exactly.
I think it's actually so. I think you are saying your picture that become heavier.
Oh, you think the QCD axion is here?
So the eigenstate you get from those mixing those two axions will make the lighter one light.
Right. Okay, good. You're thinking about the usual quantum mechanic 2x2 matrix.
But you can also solve this system to the second part. I did that practice in my mind. I think it's become.
So okay, you think the QCD axion is down here? Okay. We have made this plot. I haven't checked that. Like without it, it's.
I think it's lighter, not high.
It does make sense, but I haven't checked that. Yeah. So what I told you was wrong, then that it goes to the other direction. Yeah. But yeah, the first point we definitely have to chat about it if we want to do the UV thing. That will help me a lot.
But the first point, you just have to minimize this potential. That's all. You didn't do that.
No. I mean, you minimize this potential. That's what I was saying. That yeah, you minimize that. You will see that whatever what Jen is saying. Yeah, I minimize it. You can minimize it by leading order. That's just it. And this is just like the QCD axion that you minimize it. But Jen is saying that I should worry about fluctuations in theta 2 as well, which I'm still trying to wrap my head around. But no, sorry. Even in QCD axion, you could say that, oh, I have this potential. I have the I have essentially
one source of potential that is QCD.
But yeah, there will be fluctuations around the vacuum.
The field itself,
Right.
Into the same QCD potential, but here it's a fluctuation by another field seeing a different potential and have a different sign meaning. So your fluctuation around your own potential is the same meaning. There's no here there's another field seeing the fluctuation of another potential, the different meaning.
Okay, but it's still about the fluctuations.
So
okay.
Or in other words, I can see one potential, right?
Mhm.
I can see another potential or
Right.
a different minimum location. I want to find a global minimum.
Right.
Is my global minimum of these two potentials still at my original minimum of my first potential? The answer is likely no.
Okay. But
because these two potentials have different decay constants.
Different
periodicity.
presumably you minimize this. You didn't treat it.
yeah. You okay, again, UV side, this is the side I want to do. Okay. And yeah, I see your point. You're not talking even about the fluctuation, just the potential itself. And it's just one line. Well, I'll do it.
How you do it? You can
Yeah.
do different picture to the same.
So
again, something bridged by theta 2 is make you exposed to a different.
No, actually, even look at this thing. I see what you're saying, but look at this potential. Whatever value theta 2 has, this piece of the potential will have the minimum least contribution when this thing is 0. Talking about the potential here. Okay, So I think if you do the minimization together, like just based on that argument, you will still get 0 here. I think that part is okay. So sorry, yeah. Yeah, but all I'm saying, yeah, I agree. But I'm saying you don't even need to see this, do that. Just looking at it, you see that it goes to 0. I did it in words. Yeah, it's not a complicated thing. It's just a one function, and this is minimum when it's 0. Yeah. Okay, I misunderstood your question. Sorry, we went on an excursion because I panicked.
Let's think quickly again.
Thank you.